let me continue our networking layer module, and this time I'm going to be kind of getting back to IP addresses, and specifically IPv4 network address translation. I hope you remember this slide that I put in one of the previous parts, saying that the North America Regional Interest Registry no longer have IP address blocks to be allocated. And I mentioned briefly that there are some cheats that they did in the past, like the borrowing IP address blocks for the allocation from different registries. But even at this point of time, there's basically very few IP address blocks available globally. So, and some companies trying to cheat by like selling and buying IP addresses on a black market. So that's the basic problem. But the interesting part of the whole today's environment is we still the internet is not completely broken. I mean, there is a transition to IPv6, but it's not even close to be finished, or even half there, and yet everything is still working. And one of the key mechanisms why we're still using a lot of IPv4 addresses is network address translation. So what the people simply come up with is to have this short-term solution to effectively to solve the problem of depletion of IP addresses. So kind of what was happening initially on the internet, that was developed back then, is the fact that each host on that internet, or it was already internet, got the unique IP address, globally unique IP address. That's kind of the basic notion of kind of IP protocol. That's part of the specification. So you have to have a unique IP address in order to send packet and in order to receive packet. What NAT try to do is to hide, kind of allow you to use the private networks inside the network, like private IP addresses inside the network, but get the temporary IP address just when your packet is leaving outside world. It will be more clear after I show a few pictures. But the basic idea is that instead of using real globally routable IP addresses, you can now use these private IP addresses, and you can reuse these IP addresses in different networks. So for example, in my network, I'm using something 192.168 something, and there is a very high chance that you are using exactly the same IP address. It means nothing. We're not colliding because this is my network. The network that you're using is your network. And this IP address, this 192.168 something, will never appear on the global internet. And if it appears on the global internet, this packet will just go nowhere, like neither to me, neither to you, but just, and most likely it will be dropped on a second router. In the worst case, it will be delivered somewhere, but who knows where. At some point, the NAT mechanism is kind of considered a security measure, and for one specific reason. If you don't have a globally routable IP addresses, nobody can directly send the packet to you. So in order to actually communicate, you have to initiate the conversation, and otherwise nothing can happen. It actually creates not just security measure, but rather a few implications that I will try to discuss a few moments later. Okay, so first of all, network behind the net, like the actual network that what we have. Okay, so instead of this 192, I just randomly pick 10.0.0/8 network because it's just simpler to pronounce and simpler to write. And in my home network, I was actually trying to use this subnetwork because it's easier to write and easier to remember. Okay, so what we have here. So what we have here is simple, just one subnetwork, like my home, like a few hosts in this network, and gateway. That's it. And if I point out you to the routing table at this site, basically on each host, they will have the network address 10.0.0/, in this case I wrote 24, but it should have been 255.0.0.0. So that's it. And this network is reachable directly, and that's fine. And to send anything beyond this specific network, I have to send it via the gateway. And the gateway in this case is 10.0.0.4. That's it. That's all the configuration needed on each individual host, and that's follows the standard configuration of the routing table. What happens afterwards is if you're running NAT, there is some magic happens. And this magic simply means that as soon as the packet leaves, like whenever packet, as a host, you get the packet, you send out this packet to your gateway doing some magic with this packet, and outside the gateway, this packet now suddenly have the source address 128.76.29.7. And it has the same destination port, but again, the source address now completely different. Now, if somebody wants to send me a reply, it can easily do that by sending me a reply to this 138 address. And this packet will reach the gateway node, like our router. Again, there will be some little bit of magic happening with this packet to convert this IP address back to the original address. Like if it was a 10.0.0.1 sending, it will be converted back to 10.0.0.1 and will be delivered to 10.0.0.1. So that's kind of the basic process, what's supposed to happen if you run a NAT. One additional note here is normally all routers in the global internet, they will have explicit rule, like if you see the packet that has the destination of one of these private networks, it will immediately drop the packet. It's not always configured, but that's a normal practice on routers to have this configuration to drop packet. If someone looking from the outside of the internet to whatever packet, like observing the packets from the outside the internet, then they will not be able to even know that there are some networks behind. So they only see that this magical 138.76.29.7 is sending a lot of packets to a lot of applications, to a lot of destinations, but it will have no idea that there is one host, two hosts, three hosts, four hosts, or some other number of hosts. Take my words with like a little bit of grain of salt, because there are some kind of inference mechanisms that you can guess how many things behind the NAT, but again, it still be inference, not the kind of exact knowledge. So that's basically it. And with this concept, what you can have is you can have very big networks, like inside. For example, in one of the networks, like I think EG-ROM, if you connect it to FIU inside FIU and using EG-ROM, you will get this fake IP address, not fake, but non-routable private IP address, but you will be able to communicate to the internet. And to the internet, you will be presented as a single IP address. And that's basically the reason how you can conserve IP addresses. So all home networks kind of in the US, for example, in AT&T, on AT&T network, they will get exactly one routable IP address, like on the home gateway, and they can create any number of hosts inside the network, and everybody will be happily communicating, almost happily communicating. Okay, now a little bit of complexity. So before, what I was talking about was this magic with the packets. You got the packet from the 10.0.0.1, you do some magic, you convert it, and so forth. There's not really a magic. It's very straightforward, using some additional table. So before we're talking about the routing table, now if we do a network address translation, we do network address translation table. The entries in this table can be populated either dynamically or statically. Whenever a host inside the network is trying to send a packet, or sending a packet, so basically decided to send a packet to some host on the internet, to port 80, then a NAT box will observe this packet and will immediately create an entry in the so-called NAT table. And what it's trying to do is actually trying to remember what was the source IP address and source port, and to which to new routable source IP address and source port it was converted to. Please note that it's not just the IP addresses being converted, but rather also port numbers being potentially changed. It's not really necessary in all cases, but because multiple hosts behind the NAT are trying to communicate. So for example, 10.0.0.1 is trying to communicate, 10.0.0.2 is trying to communicate. They can potentially use the same source ports. So for example, because it's basically randomly picked port when you initiate in the connection. So 10.0.0.1 can pick port 3345, 10.0.0.2 can pick the same port. And but for the outside world, if you remember, for TCP connection, you have a 4 tuple. you actually have to distinguish this. To distinguish this, a router simply has to randomly generate additional port number. And simply like receive packet from 10.0.0.1 port 3345. It's simply picking any new available, like whatever port that are currently available, and putting its own IP address as part of this one side of the one side address. And that's it. So now this table contains this tuple of 4 items, like IP address that it was changed, the source port that it was changed, regional IP address, and a regional port. That's it. So now packet goes out, wherever it hopefully the guy on the other side generating a response, this response hopefully coming. And response will be coming again from the same IP address port that you send out before it was as part of destination. Now it's part. Before it was as part of destination. Now it's as part of the source, and destination is what was originally source. Now what the basically router is looking at is looking at the destination address and port number, matches them to the one side address entry, find out what is the LAN side of the matching entry in that specific table, and simply do the conversion. Simply convert the destination address from whatever it was originally to 10.0.0.1 and everything is happy. So note the kind of beauty of the NAT translation, or network address translation in general. So from the perspective of the internet, they just speaking with a single host, and kind of they don't do anything special. But from the perspective of the host inside the NAT, they actually not aware that any kind of a translation is actually happening. They kind of then send packet with their source IP address and receive packet with their source address, with their destination address, and everything is working happily. They absolutely have no clue that somewhere some IP address has changed, or like even how many times this IP address has changed. Because in theory, you can have multiple NAT boxes doing multiple translations, not really useful in general, because every time you just wasting amount of memory. But this is totally possible, and it will be completely transparent to you. And kind of there's actually sometimes problematic, because sometimes you want to know what is your public IP address, and you actually cannot do that on local system. You have to basically go on some website and Google what is my IP address, and only that site will actually know what is your public IP address, and kind of from that point you can guess which network you actually connected to. So let me move to problems created by NAT. And the problems, there are a few problems. So one of the kind of simple problems in this case is the complexity. I mean, because you have to not just looking at the routing table to decide what to do with the packet, but you actually have to create entry in the NAT table and kind of do rewrite of the packet and so forth. And whenever this NAT box fails, or there is some failure with the NAT table itself, for example, it overflown and not enough memory, or whatever, some other reason that there are no more space available, or that entry no longer available, then you have a problem. But that's actually not the biggest problem. So the biggest problem is running services. So as I highlighted on the slide, the communication technically starts when the host inside the network trying to send packet outside, and only then there is an entry created in the NAT table. But that's basically not it. Like, what if you want to run a mail server? What if you want to run the whatever VPN server or a web server or something? Then it's kind of in the pure NAT model, it's literally impossible, because you don't have IP addresses, you don't have globally routable IP address. Nobody can send you a packet unless you started communication. So this already hinted one of the ways you can deal with this problem, with one tiny exception that you actually don't know what port will be assigned to you, and that's a little bit problematic if you want to run some specific service. To address the problem, we have to invent so-called NAT Traversal solutions, and there are several of them. So first of all, you can have some form of statically configured NAT entries. Instead of waiting for the packet to be sent out by 10001 and the entry created with some random port, what you can do, and most of the routers, like especially home routers, they allow you to do, is to set up a kind of static entry in a NAT table. It's called different ways in different systems. Sometimes it's a port forwarding, sometimes it's a reverse NAT, or sometimes destination NAT. So they're just different names for the same thing. But effectively, it means that there's some entry, meaning saying that if I receive a packet on this port, sometimes it's just based on a port, sometimes you can also specify IP address, then you have to convert it to local kind of internal IP address and different port, or different or the same port. And for example, if you set up a web server, you basically you would need to create a kind of mapping from port 80, forwarding to one of the hosts inside the network, also on port 80, or wherever you run in your Apache server on, like inside the network. You actually don't have to run it on port 80. So that's the basic one. A little bit complex, but again, also the basic one is the universal plug-and-play protocol. And one of the reasons people actually invented this one is they got tired of manual configuration, because they want application to run, and specifically I'm talking about BitTorrent application, and they didn't want people to kind of waste their time to configure their own kind of NAT boxes, like their home routers, to get through the NAT. So basically they created this universal plug-and-play protocol that do exactly the same as static configuration. It's just there's a protocol that you can talk to your local router and simply asking, oh, please give me either random port dedicated to me, or give me some static port if that port is still available. So that's basically it. There's additional mechanisms that you can do, and it was in some point used using Skype. I think they don't actually use that anymore, but kind of given they used it before, so I'm just using it. So you can do a bit of tricks. So it's not yet UPnP. So if your router for some reason is not supporting UPnP, you still can emulate UPnP with the help of someone else on the internet. So, for example, what you can do, you can simply send a packet to some random host on the outside world, and this action of sending packet will create entry in NAT table. You don't know what exactly the entry, unless you're asking somebody else, but it will create the entry. And that relay node would actually see the kind of your source IP and source port, and that basically relay can tell you or others how you can be reached now. So we have a client trying to communicate with 10001, it cannot do it directly. It can do it via the relay, because relay has basically a connection, know how to forward packets towards the 10001, but also a client kind of just actually needs to get the information from a relay node about what is the exact NAT entry is for 10001, and it can actually send the packet directly. It's not working for all protocols, but it's definitely working for UDP, and it's actually very smoothly. It's recording some information about so in the relay node is recording information about source IP and source port associated with the user in A, whatever, and client getting that information and simply sending packets that destined to 10001 towards that IP address and port. That's it. Like that packet will arrive at the NAT router. NAT router will look at the destination IP address, destination port. It will match the NAT entry that was kind of dynamically created, and it will forward this packet properly to 10001 to whatever other ports available. So it's kind of very interesting mechanism that was explored. Doesn't require any support on the NAT router beyond doing its basic function of just creating the dynamic NAT entries, and that's it. One thing that I would like to note, like I did mention before, but NAT entries, by definition, the dynamic NAT entries are dynamic, and what I mean is they will expire if you don't send packets. So for example, if you send one single UDP packet and got response back, the entry will still be there for some amount of time. But if you don't keep sending packets to the same the same destination IP address, destination port, then this entry will be deleted. Like will disappear. Same thing for TCP and potentially other protocols if you somehow manage to run other protocols. This normally is not a big problem. Like if you actively communicating, like going to the website, downloading stuff, closing the connection. But if you're trying to do these tricks of relaying, it may create a problem, and kind of to alleviate this problem, you have to keep sending periodically packets towards the relay node, even though they serve absolutely no purpose to the relay node. You're just wasting resources, but you have to send them in order to have this NAT entry alive in the router. Or if it for some reason, for some other reason disappeared, like NAT router rebooted or something, then you have to recreate that entry over and over again. Additional note. So the example I was showing you in the picture was only included the mapping this kind of my source IP source port to new source IP source port, and that was it, and that was kind of enough. This is exactly how it works for UDP protocol, because the UDP doesn't have any other demultiplexing mechanism. So to demultiplex with UDP, it's based on a destination or just IP address and port. And depending on which side we're looking at, it would be destination or source. So it's working exactly like that. For TCP, it's not exactly like that. For TCP, we do have the demultiplexing based on 4 parameters, like destination IP, destination port, the source IP, the source port. So the NAT table for TCP connection would be a little bit more complex. So it will still have additional 2 entries. I'm not sure. I guess it's on the one side, it's still going to have not just new IP address, new port, but also include the old destination IP address and old destination port. So I think that's basically it for network address translation. As I said, it was a short-term solution to the exhaustion of the IPv4 addresses. It's kind of solved the problem of depletion, so we still can communicate, but it's actually created a bigger problem that you call it a problem, or not call it a problem, of not really having a driving force to switch to IPv6. So with IPv6, we would need the NAT in general, because we have like plenty of resources, but there is no push for that because everything is still working. The good part of NAT that I highlighted here is you are invisible to the internet. Now, invisible in terms of unless you start communicating and unless you start speaking to the internet, you basically is non-existent. Like there's no entries in that table, and there's no way to actually reach you in any way. As soon as you start communicating, there's a few holes have been poked on the NAT router as part of the NAT table, and you now at this point now other hosts on the internet can send packets to you. So some NAT entries can be created dynamically. So that's kind of the basic mechanism of NAT, where as soon as somebody started speaking, NAT entry being created. And for TCP connection, it's usually done using 6 entries, like 2 more entries than I showed on a slide. For UDP, it's the same 4 entries that I was showing, and for static or semi-dynamic entries, it's usually just 2 entries or maybe 3 entries if you map in different ports. So for example, if you're just mapping the same port to some internal IP address, then 2 entries would be enough. If you're mapping different ports, then you still have to have port that you're mapping to IP address that you're mapping, and port that be mapped to. Okay, so I hope you got a very good idea of what network address translation is, how it's being used, what the benefits of NAT, and basically what's a few problems and how to overcome them using a NAT Traversal mechanism. Okay, bye, and see you next time.